this lecture will be recorded, so that, and I'll upload it to either Moodle or probably the website more likely. If we go to the website, if you go to PowerPoints, I've already uploaded this PowerPoint to the site. And both PowerPoints, the first day and the one that we're going to go over today, are up here. And I'll add the video to this as well. Any questions, comments, or concerns? If not, I'm going to go ahead and get started. All right. Introduction to computers. So again, we'll talk about the basics of a computer, what different components make up a computer. We'll also talk about how programs fit into computing and how, when we build a program, how is that converted into machine-readable language so that the CPU, so that the machine can interpret that program and do what we're telling it to do. So we'll talk about that today. If you have any questions, just feel free to stop me when they come up. All right, so there are several different components to a modern-day computer. And this is a desktop components, but laptops have the same components, just in smaller size. Even cell phones have the same components, just much, much smaller form factor. So what makes up a computer? What does a computer consist of? So there's a CPU, so this little chip right here, there's a CPU, central processing unit. There's a heat sink and a fan, which is responsible for cooling that CPU. There's memory, where programs are stored and run from. There's hard drives and solid state drives, where we store our data. There's a power supply unit, where it's responsible for powering all these different components and converting AC current from the wall to DC current. We have our GPU, or our video card. There's actually a typo right here. Then the motherboard is what everything sits on, all these different components sit on. And then we have our communication devices, which are network interface cards, such as our Ethernet adapters and our Wi-Fi adapters. And I'll talk about each one of these in more detail in the following slides. So our CPU, the central processing unit, is basically the brains of the computer. It converts those binary instructions, so the ones and zeros that we'll talk about next time, into what we see on the screen. So when you break it down, this PowerPoint we're looking at is actually at the core, at the machine level, is actually ones and zeros, and it's being interpreted by the CPU and producing this graphic that we see here. CPUs are measured in megahertz, and 1 megahertz equals 1 million electrical pulses per second. And that's 1 million different calculations it can do per second. And that's significant, right? That's very important to the performance of a computer. That, along with memory, will increase or decrease the performance of a PC, cell phone, whatever it may be, any of those computing devices. And now, just a little bit more information. You may have heard the term quantum computing. And quantum computers, it's much different than what we typically think of a computer. Quantum computers change the actual chemistry or the physics of computing. So no longer are we looking at binary. There's actually many different combinations. Whereas binary, it's either a 1 or a 0. With quantum, it could be 1, 0, or both, or neither. There's many different combinations. And the way quantum computing works is the computer slows down those electrical pulses down to a atomic level, and it can measure those atomic differences. And that's how quantum computing works. Quantum computing is very, very expensive, but very powerful. However, it has to be programmed a specific way. So we're learning Java in this class, but there's other languages such as Python, C++, Those no longer work with quantum computing because you need specific programming for those computers. However, quantum computing is changing the face of technology. With quantum computing, it's typically used in scientific research. And in those scientific research, a lot of different combinations are possible. And so quantum computing is beneficial in those scenarios. It's also, from what I've heard and several different conferences I've attended, for cryptography, so encryption, where you're converting data into a scrambled data so that somebody else cannot read it, it's making those modern cryptographic functions or cryptographic algorithms obsolete. And so we're going to have to shift security as we know it to adjust for quantum computing in the future. Our heat sink and fan, again, responsible for cooling that CPU. There's also something called water cooling, where you're building a water loop within your PC, and it's moving water around and using that as the to transfer heat from the CPU, and then using a fan to blow that heat out of the water, similar to a vehicle radiator. If a CPU overheats, there's several different issues that could arise. One, the CPU could melt, the components on that motherboard could melt. Or the CPU, modern CPUs have something called thermal throttling, where the CPU decreases its performance in order to account for that increased heat, so as not to melt. If anybody remembers the Xbox 360 Red Ring of Death, that was because components were overheating, wasn't sufficient cooling in that device. If you've ever been into a server room or server storage area, it's usually very cold in those rooms. That's to keep all the different components cold or cool so they don't experience thermal throttling or melting. All right, now we're going to talk about memory and storage. So the reason there's different layers of storage or memory in a computer is because, one, performance, and with performance comes cost. So with a register, if you ever heard of a multi-core CPU, so maybe a dual core, a quad core, octa-core, that's the number of individual cores on one CPU. Each individual core can run independently of another. So that's additional calculations that CPU can do concurrently, right? So each individual core will have register memory. Register is the fastest memory on a PC. Very, very fast, but per megabyte, per byte, very expensive. So it's the least amount of memory, but it's the fastest. The CPU usually stores, very small instructions on those registers. The next level, one degree slower than register, is cache. Cache can be shared between the cores on one CPU. And again, you store highly accessed or data that's been accessed frequently in cache so as to speed up the process of the CPU. Cache is slower than register, faster than RAM, less expensive than a register, but way more expensive than RAM per gigabyte or per byte, whatever your measurement is. All right, then you have RAM. RAM is random access memory. One of the most important pieces of, or one of the most important components on a computer is your RAM. RAM is responsible for loading programs from storage, and then the CPU uses those loaded programs to run. So if you have any running programs, it's usually in RAM. And so RAM is obviously faster than storage, but more expensive than storage. But the way the computer works is when you first load a program, all that data is loaded into RAM. For example, I have PowerPoint open right now. When I first open PowerPoint, when I first start up the computer, it takes a while. It takes a little minute to load up PowerPoint. That's because all that data is being loaded from storage into RAM. However, if I close PowerPoint right now and try to reopen it again, it'll be much faster because some of that data is already in RAM. It doesn't have to be loaded again. Right? So that, again, that speeds up the CPU, but RAM is more expensive than storage. Another thing with RAM and cache is those are temporary storage areas. So they're volatile memory, meaning when the power is lost to a PC, all the data within those devices, within that memory, is lost. So each time you restart your computer, cache and RAM are reloaded with new data. However, storage is a permanent storage area, so a hard drive, you add data to your hard drive, you expect it to stay there once you turn off your computer. Okay? Any questions?
No.
Okay, I'll keep going. I talked about this, cache, random access memory, talked about that as well. Then you have your storage, and nowadays we have two different technologies. We have a hard drive and we have a solid state drive. Hard drive is much slower because there is a physical disk, think like a DVD, rotating within that hard drive. And so you have to access from that physical disk each time. As you remember, as you recall, or you may not recall, what's it called? Vinyl discs, what are they called? I can't even think of the name of them, but records, there we go. Records were on huge discs, but records only hold a little bit amount of data. So as technology advanced, first of all, records have gotten much smaller into DVDs, CDs, and then we advanced to solid state drives. So with a hard drive, a lot of different things can go wrong. There's a little read arm inside of a hard drive. Well, that read arm could break. That read arm could scratch your disk, and then the disk is now no longer usable. Or the disk itself could break. Again, that disk would no longer be usable, and it's slower. However, a solid state drive, all it is several flash memory modules on one device. Flash memory is the same thing you think of as a flash drive. Flash drive is one flash module. Solid state drive is you take several different flash modules and add them to the same device. Right? That's going to be faster. There are no moving parts in a solid state drives, but it is more expensive than a hard drive. However, those prices are coming down significantly. Then you have your power supply unit, which is essentially the heart of a computer. Like I said previously, it converts the AC power to DC power for the components, but it also provides reliable and consistent power to those components, right? Certain components require a specific amount of power, and that power supply provides that. You know, it converts the power from the wall and provides the requisite amount of power to those different components. In servers and large organizations, we don't want a website to no longer function because there was a power outage. For example, if there was a power outage at Google servers, you don't want Google to stop working. And California has power outages all the time. So what they have in those servers are redundant power supplies. Redundant power supplies have batteries with them so that when, in the event that there is a power outage, that battery kicks in and can run the server for a while. There are other technologies that they use in the case of a power outage, but that is a main technology, redundant power supplies. Then we have our GPU. So GPUs are great for floating point calculations. Floating points are numbers with decimals, right? Decimal numbers. Whereas non-floating point would be whole numbers, which are called integers. As you can imagine in scientific research, so if I'm doing weather prediction, there are many different variables, and those variables are not whole numbers. They are floating points. And so GPUs are really, really good, and they are specifically made for those floating point calculations. So they're very important in scientific research. If you've ever heard of cryptocurrency mining, that's a lot of floating point calculations as well. And video output in gaming. So with 4K video, so movies and things of that nature, 4K editing, A GPU is very important because in video, there aren't whole numbers. There are many different colors, many different scenes that have floating points. GPU is very important for that. Same with gaming. Gaming is basically simulating physics. And with physics, again, many different floating point calculations. So GPUs are very important for all those different areas. Then we have our motherboard that everything is stored on. Right? You have right here, these little drives are for your memory. This is where you would add your RAM. Your CPU would go right here, and then your heatsink would go on top of that. Your power supply would connect in right here, and several different areas on this motherboard. I know this graphic is pretty bad, but bear with me. Your GPU would go right here into this slot, or this slot right here. Your hard drive, solid state drive, your DVD, whatever, would connect in right here using SATA connectors. And then your network interface cards, so your Wi-Fi adapter, your Ethernet adapter, would go right here on this I/O panel. You can't see it, it's on the other side of this, but they are pre-installed on the motherboard. Then we have our communication devices. So our network interface cards, which are your Wi-Fi adapters or your Ethernet adapters. If your laptop has both, it has Ethernet and Wi-Fi, that means you have two network interface cards and two IP addresses, two MAC addresses. And so those network interface cards are responsible for generating and receiving those electrical pulses or those radio waves for Ethernet and for Wi-Fi, respectively. Each network interface card has a unique MAC address. That MAC address is assigned by the manufacturer. And the manufacturer has a portion of the MAC address specific for them, and the second portion is unique for that individual network interface card. And the MAC address is important because on local area networks, such as your home network, so in your home network, you have a router from the wall, right? The wall cable comes into your router. Then all of your individual devices, your computers, your cell phones, if it has Wi-Fi, your whatever is connected to your network, your Amazon Alexa, smart home technologies, your laptop, game system, whatever it may be, connect to that router. And all those different devices communicate using MAC addresses. That's called a local area network. So the next question is, why do I have an IP address? An IP address is so that devices across the internet can communicate. MAC addresses are only for local area networks. IP addresses are for across the internet. So for example, Google will have an IP address, your computer will have an IP address. So now they can communicate because IP addresses are routable. Okay? You can communicate across the internet. With IP addresses, you have public and private IP addresses. A public IP address is routable across the internet. A private is for your private network. So across your local area network, you'll have a private address. So your computer will have a private address most likely, but Google server will have a public because people all across the world are connecting to Google. You know, your private address, nobody's really connecting to your computer. You're typically the one initiating a connection across the internet. And your router would be responsible for translating a public IP address to your private. For example, your router would have a public address. Your individual PC would have a private. So your router would be responsible for translating its public to your PC's private. We'll talk about this more, I think next week. If you have any questions, let me know. Public, private IP addresses, MAC addresses. Any questions? Components of the PC. We're going to move on to programs now. If there's no questions, I'll keep going.
Wait, I have a question.
All right.
So when you were talking about the components of a PC, there's what's called a RAM and the ROM, right? there's a random access memory and then a ROM.
Then the ROM.
Yeah, and the ROM. So they are different, right?
Yes.
Yeah, the RAM is where you temporarily store memory whilst you're using the computer, right?
Right.
But then the functions of the ROM is it I need some clear explanation of the functions of the ROM.
The ROM.
Yeah.
So ROM is read-only memory, and let me, because I want to make sure I give you the right. Right. So I want to make sure I give you the right definition of ROM. So ROM is read-only memory, and ROM is non-volatile. So when you remove power to the computer, you don't lose that information on that ROM. Whereas read-only, a random access memory or RAM is volatile. So when you do lose, when power is lost to the computer or it's shut down, you lose all the data on RAM. So ROM is important for things that you want to be stored long-term, or you know, for more than one shutdown of the computer.
All right, thank you.
And usually ROM, the data on there doesn't change, whereas RAM, that data is changing all the time.
Thank you.
Yep. Any other questions? You can also write your questions in the chat. I have this up too as well. So if you have any questions, you can write it in the chat if you don't want to speak up. All right, let's talk about programs. So computer programs are also known as software. They're a collection, all they are a collection of instructions to the computer. So you're telling the computer, hey, store this data, calculate whatever mathematical equation, then print out that mathematical equation. All it is instructions. And obviously the CPU runs off machine language, which is 1 and 0s. But we program in high-level languages, which are much easier to read as programmers. And then, right, we program in programming languages. So very bad graphic, but bear with me because it actually tells you the differences. So we have our high-level languages, which we don't really use Fortran, C, or Pascal anymore. But we do use Java, C++, and Python. Then we have JavaScript and other scripting languages as well. We also have our low-level languages, which are assembly language, machine language, and then underneath that we have the actual physical hardware. Machine language, 1s and 0s, that's binary. Assembly language is really just one step above binary, but still tough to understand, tough to read. An assembly language, you have to know the specific hardware that you're programming for. You're writing instructions for that hardware. So the commands that you write are very specific to whatever hardware you are. So you have to know what CPU, what instructions that CPU can take or understand. What instructions can your hard drive understand? What instructions can your memory understand? What instructions, and so on and so forth. Whereas with our high-level languages, we write almost English-like, and the compiler or scripter, interpreter, is responsible for translating that down to machine language. Makes it a little bit easier for programmers. And now we don't have to focus on knowing specifically what hardware we're programming on. Now we're free to create very advanced programs that do much more for end users. Here's our different levels of programming. Like I said, assembly language versus machine language. Please don't ask me what that is saying because I don't understand assembly language. But that is the code. As a programmer, you would need to know that. Then you have an assembler plus a linker to convert that to machine language. People don't necessarily program in assembly language anymore because it's so specific, and you have to know exactly what you're programming for. The only people I can think of that actually use assembly language are those that make hardware devices. So if I'm creating a new type of solid state drive, I would write the firmware for it in assembly language so that other programs can access it. Here are some of the drawbacks of assembly language. It's susceptible to errors. Because you have to know the specific hardware, and there are so many things that you can mistakenly write, there's no telling how many different errors you can put into it. So you have to be perfect when you write in assembly language. And now we have more advanced languages, so we don't necessarily write in assembly language anymore. All right, we have our high level languages. So easier to learn than assembly, not necessarily easy to learn. Some examples are Java, C++, Python. So Java and C++ are considered compiled languages. And I'll talk about that in the next slide. But compiled languages, you have a compiler that converts what you write as a programmer into the machine readable code or machine executable code so that the actual machine could run what you're trying to tell it to do. Java is basically a evolution of C++. The main difference, and we'll talk about this, I believe, next week when we discuss Introduction to Java, but the main difference is Java has something called a Java virtual machine. So the Java virtual machine is responsible for knowing the specific hardware that you're writing your program on. And then you can write your Java program. The Java program that you write runs on the Java virtual machine. The Java virtual machine is then responsible for the hardware, okay? Whereas with C++, the program you write goes straight to the hardware. So you kind of have to know what type of hardware, what type of operating system you're writing your program for. So that makes Java, all you have to do is install the JVM, Java Virtual Machine, on whatever device that you're trying to code for. And then your program will work on any device that has a JVM running on it. Whereas C++, you would have to recompile your program each time because it's a new piece of hardware. Then Python, JavaScript, and several other, I think Go is another one. These are called interpreted languages or scripting languages, whatever. And what those are, at runtime, they are interpreted, and the interpreter is responsible for converting it to machine language and running it on the machine. Since Java and C++ are compiled languages, you first have to compile them and then run them. Whereas Python, JavaScript are interpreted languages, so you don't have to compile them, you just run them, and the interpreter is responsible for doing all the compilation. And it's debatable performance-wise, which is better. There's a competition between the two, but usually compiled languages are faster because at runtime you don't have to go through all that interpretation. So here's an example, Java example of what we would do. It's a lot simpler, a lot more readable than that assembly language earlier. So what are we trying to do here? So first, we have a radius. All we're doing is trying to calculate the area of a circle, right? So what do you need? First, you need the radius. So we're setting radius equal to 20. We have a radius of 20. And then area equals pi r squared. So pi r squared is radius times pi. That's what we're doing here. We set that equal to area. And then we system.out.println, and all this does is print out the results. And what it will say is the area for the circle of radius, we add in that radius variable, is, and then we add in the area variable. And there you go. A lot more readable than assembly. And as we go throughout the class, you'll do this and more. But this is just a quick introduction, a quick display of what those high-level languages are and why they're popular now. So with assembly language, there would be a lot more commands, a lot more lines of code than what you see here. All right, so I kind of talked about this, but much higher productivity, lower risk for errors because you don't have to know specific hardware instructions to run your code. And like I was saying earlier, there's a compiler. This right here is C++ code. So we write our C++ code, we compile it into executable code, and this is what the machine reads. Like I was saying, everything you do on your computer, when it's broken down, when it's compiled into ones and zeros, and that's what the computer reads. And it converts it to what we see on our screens. It's really quite amazing. All right. And that'll do it for today. Any questions? You can write in the chat. You can speak up if you like. If there aren't any questions, that is the end of class. If you do have any questions, just shoot me an email and I'll respond as soon as possible. Other than that, have a good one. Be safe.
Somebody have a question.
Okay. Go for it.
Did you see it? No, somebody wrote it in the message.
Oh, okay, I got you. Actually, next class will be dedicated to converting binary to decimal. So we'll cover that next class.
And our quiz is due today still, right?
I'm going to extend it till Sunday.
Extend it till Sunday. Okay.
Yeah, we'll actually go over converting binary to decimal and moreover IP addresses and MAC addresses. Hexadecimal as well is another conversion. So we'll talk about all of that.
All right. Have a good day.
All right, you too.